Before we talk about the fundamental theorem of calculus, I'd like to review the mean value theorem. As it turns out, we'll use this to prove the fundamental theorem of calculus. So just to go back to a Calc 1 topic, Rolle's theorem, if we recall what that says, what we're going to do is suppose that we have our function f that is equal to 0 at both x equals a and x equals b, and also that f of x is differentiable, at least on our interval from a to b. Then the conclusion is that there must be a point C in the interval from a to b such that the derivative of f at C is equal to 0. So a couple things to think about here. We can visualize this first of all. If I think about my axes, and let's suppose that this is A and this is B, and we have a function that passes through the x-axis at those points. Then what this is saying is that we could consider that in order for f to start at 0 at A and then end up there at B, we have to, in some sense, turn around somewhere along the way. So for instance, right, we could have a function that looks like this. Alternatively, right, the function could do something like this. But essentially, what would have to happen is that somewhere we would have to be able to find a tangent line that's horizontal. And I'll point out one thing that we'll often do in this course is we want to focus on the requirements. So we not only said that f had to be 0 at a and b, but the other thing we specified in here was the idea that f is differentiable. So for instance, think about a function that has a corner, right? So if I were to draw a function that passed through 0 at a and at b, but had a sharp corner, then I might actually not have a place in between where the derivative is 0. Okay, so starting with Rolle's theorem and moving to the mean value theorem, in some sense we're going to loosen the original assumptions. So at this point, what I want to consider is, suppose that we no longer have the assumption that f of a is equal to 0, as is f of b. So we're still going to assume that our function is differentiable. But now, what can we say? So what we're going to do is I'm going to define a new function, g of x. And g of x is going to be the function f of x minus f of b minus f of a all over b minus a. So that constant times x minus a plus f of a. So to be clear, I do not expect that you know where that function definition came from. So as I proceed through these next steps, we're going to have this function in front of us, and we want to check a few things about g of x. So first of all, let's consider what happens when we plug in x equals a to the function g. So keep in mind that there are a lot of constants in here, but I'm focusing just on where the x's are. So if I plug in a, there's really two places that I need to plug this in, right? So there's an x here and an x here. So plugging in a in place of that, I get f of a here. This constant is the same. I get an a here, and this constant remains the same. Now, what we can consider is a minus a is 0. So this goes away. And consequently, this whole product goes away. And what's left is f of a minus f of a. I've got to distribute that negative sign. And this then becomes 0. Let's consider the same thing, but now let's plug in b. So coming back to g, I'm going to plug in b once again for the two places where x shows up. I get f of b minus the constant times b minus a plus f of a. Now in this case, what I can do is I can cancel this denominator with this multiplier. And then if we're careful in distributing the negative sign, let's see what we have left. We have f of b minus f of b minus f of a. And then within this parentheses, I'm still adding f of a. So again, notice that I have inside of here a negative f of a and a positive f of a. I have a positive f of b, and I'm subtracting f of b. So once again, I get 0. So now we see that our function g of x that I've constructed does pass through 0 at x equals a and x equals b. So if we come back to Rolle's theorem, maybe we can apply Rolle's theorem to g of x. The only other thing we need to ensure is that g is differentiable. And so if we assume, which I said we will in the beginning, that f is differentiable, notice that g is as well. And we can actually compute that derivative. So g prime of x, if you come back to this definition of g, keep in mind again what is constant. So f of b minus f of a over b minus a is constant, f of a is constant. So in taking the derivative of g, I'm going to get f prime of x. And then essentially what I'm subtracting in the parentheses here, or the square brackets, that is a linear function. And so the derivative of that linear function is simply this slope value, the constant multiplier in front of x minus a. So this is g prime of x. So at this point, we have that g of x is differentiable, and likewise that g of a is 0 is equal to g of b. So Rolle's theorem implies that there is some value c and c has to be in our interval from a to b such that g prime of c is equal to 0. So again, that's just the direct statement of Rolle's theorem. And let's think about what that means. So we found g prime of x. So if g prime of c is equal to 0, that means that, let's plug in c for our g prime of x function, f prime of c minus f of b minus f of a divided by b minus a should be 0. And if I rearrange this, this says that f prime of c is equal to f of b minus f of a over b minus a. So thinking about what that means is that if we look at these here, on the one hand, this is the slope of the line tangent to f of x at x equals c. On the other hand, this is also a slope. This is the slope of the secant line connecting 2 points on the graph of f, in particular a f of a and b f of b. So we can actually visualize what this is saying. So in this instance, remember our f function is not assumed to pass through 0 at a and b, but instead we just have some arbitrary function. So here's my f of x. Let's suppose a is here and b is here. So we can find the requisite points. So what we're saying is I can find, first of all, the secant line we're describing. So I find my 2 points and I can connect those. And so that line has slope f of b minus f of a over b minus a. The claim is, as long as my function is differentiable, I should be able to identify some value, possibly many values, between a and b, so at least one, some value c, such that the line tangent to f at that value essentially is parallel to the red line, so they have the same slope. If you were to follow along with your pencil, you could identify eventually that it looks like maybe if I were to find the line tangent here, those look roughly parallel. So in my picture, a c value that would work would be here. And like I said, it might be that you find multiple points for which that's true, but there should be at least one. So what we've identified here is exactly what the mean value theorem states. So we've gone through the derivation based off of Rolle's theorem, and I'll just finish here to make sure that I concisely write up what the statement of the theorem is. So the mean value theorem, we just need to start with the assumption that our function is differentiable on the interval at hand. So if f is differentiable on the interval from a to b, then there is a point c in the interval from a to b such that f prime of c is equal to f of b minus f of a, all divided by b minus a. So that's the statement of the mean value theorem. And again, the reason I'm introducing this here is that in the next video, we want to actually derive the fundamental theorem of calculus, and that's going to rely on our knowledge of the mean value theorem.